Hello and welcome to this video in which I model and solve uniform motion problems. Okay, so when they say, uniform motion, it just means that everything that moves in the problem we're going to assume is moving at a constant speed. Right, so something that's something in the problem, if it's going 50 miles per hour, it's always going 50 miles per hour. Or if something's going 20 meters per second, it's always going 20 meters per second. So that's what they mean by uniform motion. And throughout these problems, I have a couple examples for you today. We'll be working with the principle, using the principle that the distance traveled is equal to the speed or rate at which you travel multiplied by the time you travel for. Or distance equals rate times time, or speed times time. That is a key principle that will be employed throughout the working of these problems. So let me begin. So the first of these two examples I've got for you involving uniform motion. I have a small airplane, can travel 120 miles per hour, or mph for short, in still air. All that means is, with no wind blowing from its back, not going with the wind, and no wind blowing toward it, in the front of it. And so this is neither with nor against the wind. It's in still air. The plane can fly 700 miles with the wind. Alright, with the wind means that the wind is assisting you. The wind's at your back. It's speeding you up. So we'll have our speed in still air, and then also the wind speed assisting us with the wind. Alright, so the plane can fly 700 miles with the wind. In the same time, it can travel 500 miles against the wind. Alright, so against the wind means the wind's at your face, whatever, you have your speed in still air, and then going against the wind, that speed is decreased by the wind speed. Alright, you're slowing down. You're getting slowed down by the wind. So we're asked to find the speed of the wind. As I mentioned at the opening of this video, everything in these problems we're going to consider is moving at a constant speed, right? So the wind, wind changes in real life. Wind speed changes quite often. But in this problem, we're going to consider the wind to have a constant speed. Alright, so I've read through the problem. Explain what a few things mean: with the wind, against the wind. They're asking us to find the speed of the wind. So I read through the problem. You want to know what do they want? What don't I know? Okay, so this speed of the wind, I'm going to call that W for wind. Right. So I'm going to say let the variable W represent the speed of the wind. And I'll have that speed be, since all the other speeds, the only other speed here that was mentioned is this 120 miles per hour. Speed is a rate of travel, right? Miles per hour, miles for every hour. So I'll say that the speed of the wind is going to be in miles per hour too. All right. Alright, so let's look at a couple things. This problem describes a couple trips this plane takes. And throughout this problem, in all these uniform motion problems, we're going to be employing the following principle. The fact that the distance you travel for, distance is equal to the rate at which you travel, or the speed. Right? Speed is just sometimes called rate of speed, or the rate at which you travel, multiplied by the time that that trip takes, the time that you travel for. So please keep this in mind as we work through this. Now I'll read back through the problem again, and the problem talks about 2 trips. There is 1 trip with the wind, so let's talk about that. Okay, so all that means is that the speed of the plane is, increased by the speed of the wind. The wind is at your back. You're going faster. All right. So that trip with the wind is mentioned in this part of this sentence, right? The plane can fly 700 miles with the wind, and then it mentions the trip against the wind. All right. So the distance traveled, that's 700. I'll put 700. You can put the units in there if you want, 700 miles, but that's 700. All right, equals the rate at which you travel for. Now, I hope this makes sense. Now, I don't really know how fast you're going with the wind, but I'll call this R sub W for the rate at which the wind you're traveling with the wind. R sub W is going to be basically the speed in still air. Right? So the still air speed, right? How fast the plane goes without wind, and as I mentioned, that speed is increased, right? So when you're going with the wind, I would add to that the wind speed. Right, so I do have an expression for this. The rate at which the plane is traveling with the wind would be 120 miles per hour, right? That's how fast it's going in still air. And then on top of that, the speed of the wind, right? As we're going with it, the speed of our plane is increased by W, right? The W is the speed of the wind. So that whole thing is going to replace the rate. And whenever you replace things, and what you're replacing with has multiple terms like this, 120 plus W has 2 terms, get in the habit of putting parentheses around that, around what you've replaced. So the whole thing, 120 plus W, is the rate at which you travel for, multiplied by the time. Now, the time is not mentioned, and that's okay. Let's call it something. So let's say, I'll call it a lowercase t. So let's say lowercase t is the time traveled. Right, the time it takes for the plane to go 700 miles. Right? Time for the plane to go 700 miles. Right? So that's times the t. All right. So I'm going to do this now. You're going to see why, because I don't really want t involved. Right? We're trying to find the speed of the wind. So what I'm going to do here is I'm going to solve this for t. So we have t equals, and then then an expression that doesn't involve t, and all that would take here is dividing by 120 plus w. So t, the time, if distance equals rate times time, then the time it takes to go that distance would be the distance divided by the rate. So the distance divided by the speed. So 700 divided by the whole 120 plus w, right? So let's keep that in mind, right? This isn't the answer or anything. I'm just bubbling, and I'm going to keep that in mind when we move on to the next trip. All right. So the next trip mentioned is the going against the wind. Right? They talk about the plane can fly 700 miles with the wind, and in the same time it can travel 500 miles against the wind. So make another little line here for talking about the trip against the wind. So same principle, right? We're working with this distance equals rate times time. The distance traveled this time is 500 miles, right? So the left side I got 500 equals, and then this time, the rate, the speed that they're going when you're going against the wind. When you're going against the wind, the speed of the wind decreases your still air speed or your normal speed. So I'll call this R sub A for speed rate against the wind, and that's just going to be our still air speed. And this is, I'm going against the wind, so we'll subtract from that the wind speed. Right? The wind speed will be decreasing our normal speed. Well, we know the still air speed was 120 miles per hour. And I'm taking away the wind speed, and again we called the wind speed W. And it's, again, all of this, right? The quantity 120 minus W would replace the rate. Now here's the tricky thing, multiply by the time. There were some key words, right? And you gotta kind of pay attention. There were some key words mentioned in the problem. Those key words were right here. The plane can fly 700 miles with the wind in the same time it takes to travel, 500 miles against the wind. So this T I put here in the on the first page, this is the time traveled, for both trips. Like it takes T hours for it to go 700 miles with the wind, and it would take that same T hours, right? In the same time, it takes that same T hours to go the 500 miles against the wind. All right. And again, I don't really want to solve for, I don't want T involved. So I'm going to try to, we'll solve for T here to get it in terms of just, things without T. And that would be the distance divided by the rate, 500 divided by 120 minus W. Alright, and keep this in mind as well. Again, not the answer. We haven't solved for W yet. Well, really what I have here is what's called a system of equations. This is a system of two equations with two variables. And the reason I solve for T is hopefully more apparent now. What I'm going to be doing is a substitution. Right? Because as I said a second ago, the T up here is the same time as the T down here, right? Because both trips are taken in the same amount of time. So this T is equal to this T, meaning I can replace this T with this expression, or I could replace this T with that expression. They're both the same. So when I replace the T, anytime I see a T, I can replace it by 700 over 120 plus W. I'm going to do that down here, and we'll end up with a proportion, right? An equation where two fractions are equal. So after substituting, we end up with this this proportion. I'd have the 700 over 120 plus W replaces the T down here. We have 700 over 120 plus W equals, and then the other side, I replaced this T down here. The other side is this fraction, 500 over 120 minus W. Great. Alright, then we have a proportion to solve, right? Some equation with some fractions. Now you could do the product of the extremes equals the product of the means, right? Set up the cross products. And you'd end up with this right here. You'd have 700 times the quantity 120 minus W, right? That's the extremes, equals 500 times the entire 120 plus W, right? So the whole thing in parentheses, right? The 500, that's the means. And I would have gotten the same thing if I multiply both sides by the least common denominator as well. Right? The LCD would just be 120 plus W times 120 minus W. Right? And the only way this can happen too is if W is not negative 120. I'll make that little note off to the side. Or positive 120, because you can't divide by 0. Right? So as long as W is not one of these things, we're golden. Alright, then continuing on, I solved this equation. Now, just to shrink some numbers down here, I notice a common factor on both sides. You know, this is 7 times 100. If I divide this by 100, and this is 5 times 100 here, so I divide both sides by 100, and that'll get rid of the factors of 100. And I'll have this equation now, you know, 7, right? 100 goes into 700 7 times, and then so I'd have 7 times the 120 minus W equals, and then the same thing over here, 5. 100 goes into 5 times. I'd have 5 times the quantity 120 plus W. And then we'll do some distributing. Right. So 7 times the 120 minus 7 times W. So 7 times 120, that'd be 840 minus 7W equals, and then over here I'm distributing the 5. Alright, and then 5 times 120 is 600 plus the 5W. Then to get all the, you know, it's a linear equation in W, so then I get all the terms with W on one side. So I'm going to take them all to the right, so I get a positive coefficient for my W. Add 7W to both sides. And I'll have all the W's on the right, so I'll take away the 600, this term without a W, take that to the left side. So subtracting 600 from both sides. That leaves me over here with 240, right? 840 minus 600 equals, and then over here 5W plus 7W is 12W, and then finally divide by 12 on both sides, or multiply by 1/12. And you know, 12 goes into 24 twice, and you also have a factor of 10, right? So this is 20. W equals 20. And then let's make sure that that actually satisfies our original equation up here. You know, when I replace 20 with W with 20, this would be 700 divided by, you know, 140, 120 plus 20, and that'd be, you know, that'd be 5. And then this would be 500 divided by 100, which would also be 5. You get 5 equals 5. This is a good solution right here. So I've solved for W, but you know, again, it's a word problem, and you should answer word problems in complete sentences and have units, so it gives the numbers meaning. So this is great and everything, but it's not how I'm going to answer the question, right? They said find the speed of the wind. And that's what this W represented, right? W represents the speed of the wind in miles per hour, so this means 20 miles per hour here. So the way I'm going to write the answer for this is, you know, the speed of the wind is 20 miles per hour. I'll just do MPH. Right, complete sentence. And all the numbers I mentioned have units attached, so that it gives them meaning. Right, this is how you should be answering all your word problems. All right. So again, this whole time I just looked at, you know, what information was given to me. Like, you know, keywords pop up, and the keywords in one problem aren't going to be the keywords in another problem. You're going to have to really pay attention. I understand it is difficult, you know, that's why you just got to keep practicing. You got to keep seeing more and more of these things to get used to how things are worded. You know, when are you you know, be able to recognize when you're seeing keywords. Hopefully with enough practice you'll be able to do that. But you know, I noticed that I was, you know, given information about 2 trips, and then I broke those 2 trips down using this same principle each time, that the fact that the distance you travel for is equal to the speed that you travel for, or the rate that you travel at, multiplied by the time that you travel for. And that's going to continue to work in my next example as well. Okay, so the next example I've got is another word problem here, involving, you know, distance and speeds and, you know, traveling. This one's running and walking. To prepare for a marathon run, Sue ran 18 miles before she blistered her heel, and then she walked 1 additional mile, right? So for a total of 19 miles. Her running speed was 12 times faster than her walking speed. She was running and walking for a total of 5 hours, right? So the 18 miles and then that 1 additional mile lasted 5 hours. Find Sue's running speed, right? So again, that's what's being asked for, right? Sue's running speed. So I'll call that something. So I'll let just S for. Maybe I'll call it R, because we do have a walking speed that's also mentioned, right? She's running, she's walking. They're asking for the running speed. I'll call it R instead. So this is Sue's running speed. Whenever you see this lowercase r, this is Sue's running speed. And in what units would that be? Let's see. All the distances are mentioned in miles, and all the times that are mentioned are in hours, right? The 5 hours. So miles per hour, again, just mph. All right, because again, a speed is a rate, miles per hour, meters per second. All right. Okay, wonderful. And then, and I did mention too, there's this walking speed. I know we don't have to find the walking speed, but she's running at one speed and walking at another speed. All right, running the same speed the whole time and then walking the same speed the whole time. So if I want, I could call that W, Sue's walking speed. And then later we'll see a little relationship, right? They did mention a relationship right here between her running speed and walking speed, right? Her running speed is 12 times as fast as her walking speed. We'll use that in a little bit, okay? So our walking speed in miles per hour, all right? Okay. And again, don't forget our little principle that's going to be used throughout. The distance traveled is equal to the rate of speed multiplied by the time you travel for. Okay. Alright, so then I read back through it again and I notice, there are 2 parts to this trip. Right? There are 2 parts to this trip, just like there were 2 trips in the first example. Right? One with the wind, one against the wind. This time it looks like it's broken up into running, her trip running, and then her trip walking. So let's look at running. Right. So her trip while running. We have a distance. I'm using this little principle here, this equation, this formula. It says she ran 18 miles and then started walking after blistering her heel. So I've got 18 there for the distance, right, equals, and then the rate at which she runs. Okay, I don't know that. That's what we're trying to find. I'm calling that R. Remember, her Sue's running speed. And the time that she travels for in that first while running, I don't know that either. Okay, I do not know the time that she ran for. All we know is the time that she ran and walked for, right? The total trip took 5 hours. All right, so here's another variable I'm going to introduce, right? Anytime you come across an unknown, it can't hurt to assign a variable to that thing. So I'm going to let just, lowercase t, maybe even t with a subscript of run. Right, so because I might do the same thing for walking, right? So I'll let t run be the time, t sub run be the time she ran for, and the total time was mentioned in hours, so I'll say this is in hours as well. So her running, she ran 18 equals, the rate her running speed was R times and then T run. Right. Okay, and this is really all I'm going to go with right now. Right? And you're going to see we're going to set up a couple equations, a system of equations, and break it down to just a couple variables. All right. So now the next one. All right, that's a little equation involving her running, but she also walked. Right? She had a part of the trip where she was walking. So the walking part of the trip, well, they only said she walked. I'll get this equation down. We'll come back to that in a little bit. The walking equation. She walked for 1 additional mile. So her distance walking, 1 mile. The rate at which she walked. Now, this is where you can use W, right? So remember, the W was the speed at which she walked, the rate at which she walked. So I can use W for rate if I wanted to. And then the same thing goes for the time. Now I'm going to let here, I don't know how long she walked for. Again, we only know how long she ran and walked for. So I'm going to let T sub walk be the time she walked for in hours, right? Everything's in hours here, all the times. So the 1 equals W times, T walk. And this is great. I mean, it's fine for now, but it does cause a little bit of a problem. Because those are the only 2 equations I can seem to write until we get to the next, sentence, next couple sentences. So you see right now I have, 2 equations with 1, 2, 3, 4 variables, right? T run and T walk are different variables. Yes, they both have T, but they have different subscripts. I would like the number of equations to be the same as the number of variables, right? So then we can make substitutions and eventually, solve for the one that we want, the R, right? I eventually want the value of R, her running speed. All right. So I got an equation about her running trip, got an equation about her walking trip, but I'd like to limit the number of variables, right? I don't like the fact that there's 4 variables in these 2 equations, more variables than there are equations. That's not nice. So I'm looking at the next sentences. All right, we did the running trip, we did the walking trip, that was mentioned in this sentence. The next sentence gives us a way to get rid of one of these variables. It's a relationship between her running speed and her walking speed. All right, so we're told here that her running speed was 12 times as fast as her walking speed. So that tells me that, so here's the next sentence. So here's a relationship between running and walking speed. You can get some relationships down here. Her running speed, R, is, was, is. Anytime you see was, is, are, in a sentence, in a word problem, usually it implies equals. To the verb to be will usually imply equals in some statement. So her running speed R, that we called R, was or is equals, and then 12 times her walking speed. So 12 times W. So if you'd like, you can go back up to one of my equations earlier for the running trip or the walking trip. I can replace R with 12 times W. But if I do that, that'll eliminate R. That'll make this 12W. But I want to eventually solve for R. I mean, you can do that, it's fine. But we can manipulate this as well. If I say that her running speed is 12 times her walking speed, you could also divide both sides by 12 and say that her running speed divided by 12 is the same as her walking speed. And now I have it solved for W, and I can do this. I can replace, anywhere there's a W in this problem, I can replace W with R over 12, and that's what I'm going to do down here. I'm going to replace this W with r divided by 12, and that'll get rid of the w in my equations for the two trips and leave me with just r's. Okay, and then the same thing goes for the time, right? The very next sentence in the problem, she was running and walking for a total of 5 hours. Right. So we have the time she ran for called t run, the time she walked for called t walk. There is a relationship between those two too, right? So the time she ran for, which I called t run, right, t sub run, on top of that, add to that the time she walked for, and that's going to be equal to 5 hours. Right, that's what that sentence said, right? She was running and walking for a total of 5 hours. Okay, so this again gives me another way to kind of rewrite the two equations. So if I'm replacing w with r over 12, I can replace t run or t walk if I wanted to, and then I'll have a couple equations with a couple of variables. All right, so let's check it out. Just solve for one of these, right? Like I did here. This was solve for r or solve for w. If I simply subtract t walk from both sides, say t run equals 5 minus t walk. Right. Or you can solve for t walk. Say t walk, L equals, subtract t run is 5 minus t run. That would be fine as well. And in fact, I'm going to do that just so I can stick things on the same page here. All right. So anywhere I see a t walk, the time it took her to walk that mile, I can tap this on, and there's t walk in that equation, right? In her equation for the walking trip. Alright, so let's see what that all looks like on the next page. Alright, so on the next page I'm going to have two equations with two variables. Alright, so let's go back to our running trip. Alright, so the running trip I didn't really change. Alright, if you look back at the running trip equation, I still have 18. The 18 miles equals her running speed multiplied by, the time it took her to run. That t run variable. It's the walking trip that I changed. Right? The walking trip, I had the 1 mile equals, and then the walking speed we are going to replace with, the running speed divided by 12. And that's being multiplied by the time it took her to walk that mile. That's being replaced by 5 minus the time it took her to run. The whole thing, right? So that whole thing of the 5 minus the time it took her to run is going to be parentheses. So instead of t walk here, I have 5 minus and then the time it took her to run. Great. Alright, so now what I have here is a much nicer looking system with a lot fewer variables, right? This is two equations, two variables, much better for me than 4 equations and 2 variables. And we can use this to solve for r, right? I can make a little substitution here. See, there's t run. Let's just take one of these equations. When you have a system of equations, you can solve it with try solving them with a lot of substitution. So that top equation there, if I solve for t run, right, that top equation, if I solved for the time it took her to run the 18 miles, that would be equal to 18 divided by r. right? And then, oh look, I see the same T run, the time it took her to run the 18 miles, down here in this equation. So we'll make a substitution. This T run I can replace with the 18 over R. And if I do that, look at what this second equation, this walking equation, becomes. All right, this walking equation now becomes 1 on the left side equals, you have R over 12 times the quantity 5 minus and then 18 over R. And look at what I have right now. All right, now I have a single equation with a single variable, and that variable is R, the thing we're trying to find, right? R is Sue's running speed. Okay, so let's do this. Now I'm going to point out off to the side that R can't be 0 here, right? You can't divide by 0, and then we'll go through and solve this equation. All right, I'm going to have to distribute this. Just clear some parentheses here. So I've got 1 on the left equals, this first term would be 5R over 12, or 5/12 R, 5/12 times R, minus, and then the second, when I multiply the second fraction, you see a factor of R in the denominator, R in the numerator. The R's would cancel, and I'd be left with just 18 over 12, right? But 18 over 12 reduces to 3 halves, right? That's 6 times 3, that's 6 times 2. The factor of 6 would cancel. All right, and now I have a real nice equation. Just add 3 halves. Now if you don't like the fractions, you might say, hey, the LCD is 12, and then multiply both sides by 12. All right, multiply both sides by the LCD. There's 2 terms over here, so I'd have to distribute. And then we get this equation without some fractions, right? You'd have 12 on the left side equals, and then when I multiply the first fraction by 12, the 12's cancel. I'm left with 5R minus, when I multiply the second fraction here by 12, 2 goes into 12 6 times, so you'd have 3 times 6 left over, or 18. Then we'd have to get all the terms with R. It's a linear equation in R. I'd add 18 to both sides to get all the terms without R on the one side, terms with R on the other. So it's 30 equals 5R, and then divide by 5, and 30 divided by 5 is 6, and this is R, so R equals 6. And then let's double check this back in our original equation involving just R. That was this guy up here. 6, that's a half, and then 5 minus 3, half of 2 is 2, half of 2 is 1. That works. All right, this is a valid solution for this equation here. But let's see if it actually, makes sense with the problem, right? So after all this, what we're saying is, Sue ran 6 miles per hour. Right? Remember, that's what we're trying to find. That's what R represented. R represented Sue's running speed, and it was in miles per hour. So remember, to finish off word problems, to solve word problems, you must answer, please, in full and complete sentences, and put units on your numbers so that they have meaning. So this isn't the answer totally. The way I'm going to actually answer this is that Sue's running speed was 6 miles per hour, right? mph. And this is how I would answer if I was given this on in a math, in an exercise set or something for a math class. All right, so that was a lot, I know, but it goes to, it has all the principles of some problem solving in there. You read through the problems, you read through a word problem, and anytime you come across something you don't know or that they're asking you for, call it something. Like I called Sue's running speed R. I didn't know walking speed. I called it W. Later I didn't know the time that it took her to run the 18 miles, so I called that, T run. I didn't know the time it took her to walk the 1 mile, called that T walk. And, Just be wary though. The more variables you assign, the more letters you introduce, the more variables you have, the more equations you're going to need to write to be able to make anything of it. Because if you have too many variables and too few equations, very often there's like infinitely many possible outcomes you could see. And if you have too many equations and too few variables, something might not come of it at all, or there might be infinitely many solutions again. There's lots of ways to say that. But notice how when I introduce 1, 2, right, 3 and 4 variables here, right, and I ended up with 1, 2, 3, 4 equations, right? Typically in these beginning algebra, intermediate algebra, the number of variables you introduce should be the same as the number of equations you can write. And through some substitutions, some clever substitutions, you'll be able to solve for whatever variable you need to. All right. So yes, it was very convoluted, but that is going to be the case in some problems. You're going to come across ones that aren't very direct, aren't very straightforward, and you're going to have to mess around with them, make substitutions, set up many equations and many variables, and hopefully eventually you'll tackle it. All right. So just keep practicing is all I can say. All right. The more you see, the better you get at them. All right. And just don't forget too, for uniform motion, anytime they talk about somebody moving, things moving at the same speed, constant speeds, that principle of distance equals rate times time is paramount. It's key. Okay, so that's about it for this. And like I always like to say, try your best to pick up the material, understand the material on your own before you go out looking for help. So I find that it tends to stick better. People tend to remember things better when they've taken the time and put forth the effort and the blood, sweat, and tears to get it on their own. They feel more proud of themselves, more proud of the work. So read the material first and foremost. Please read your books, read your material. Read through the author's examples. Sometimes even try to work out the solutions to an example before you even read what the author did. Maybe you'll learn from some mistakes there, or surprise yourself. Of course, practice exercises, plenty of them. Practice problems, and try to find ones that you can find solutions for, whether it be in the back of a book or on some worksheet or online even, just to check yourself. And don't give up after the first shot. Don't get so easily frustrated. If after several attempts at a problem you're still not getting it, walk away from it for a second. Maybe go back and read the material again. Maybe even read it a third time, more slowly, more deliberately. And perhaps you'll come across something in the second or third reading that you didn't the first time. Something will click that didn't click before, and it'll make the problems easier. Who knows? I'm hoping so. But if after several read-throughs of the material and several attempts at a problem or two or many, you're still not getting it, then it is not a sign of weakness whatsoever to go out looking for help. That is what other people are there for. So ask a teacher, ask a tutor, ask a friend, someone in your class who you feel knows the material well and has time to help. Look for supplemental materials online. Look for videos, maybe videos such as this one, or plenty of other videos out there that are better than this one. I promise you'll be able to find them. Just keep searching, and just keep at it. Stay persistent. Keep practicing. Keep putting in the time, the effort, and I know you'll eventually get it. And also try to have fun with it too. Try to have a positive attitude. It's amazing the difference a positive attitude can make, instead of just going into something thinking you're going to hate it. Just go in with an open mind. Go in with a positive attitude. Feel like you're going to learn something and that you're going to enjoy learning something, and see what kind of a difference that makes. So keep at it. Keep practicing. Try to have fun with it. And thank you for watching.